going to look at the IR spectra, okay, for the interpretation. First two examples showing here are the IR spectra of alkane. First compound is an octane and the second compound is an hexane. So they are quite similar. So after you can see the spectra of a compound, what you have to do first is identifying the chemical bonding, right? But what kind of chemical bonding you can observe here? First of all, as I said, there are fields of characteristic position of the graph. Okay, in here, what you can be easily noticed is the 3000 wave number. At 3000 wave number, normally this is the borderline to distinguish between alkane, alkene, and alkyne. So if the absorption is under 3000, this is the characteristic absorption peak of the alkane, or actually is the sp3 carbon stretching with the hydrogen atom, right? So it's the alkane. So I will remark here sp3 carbon single bond with alkane. This is this character, and also under below 1500 are the characteristic are the fingerprint region. So we normally ignore them because, as you can see here, they remarked as bending of hydrocarbon, which is actually we have normally in organic compound, as you know, we have the R group, right? And the R group contains CC bond and CH bond, and they can have kind of rocking, bending, everything, and they normally appear here beneath the 1500. So in every organic molecule contains this kind of thing with very complicated fingerprint. So we normally ignore them. Next is the N-hexane. As you can see, we cannot distinguish between N-hexane and N-octane because the chemical bonding here in the structures are very almost exactly the same, I would say. So we cannot use this technique, IR spectra, in order to characterize the differences of these two compounds. We need something else, actually the NMR, that we are going to talk about it later. Now we're going to move to the next type of compound, which is alkene. And as I said, first of all, you have to mark 3000 wave number to see whether you have alkane, alkene, or alkyne. And this is 3000 something, right? Here, 3000 something, 3080 to be exact, is the sp2 carbon single bond with hydrogen. This stretching is appeared beyond 3000, a little bit beyond 3000. Okay, and you have to be double checked or confirmed with the double bond region, because the alkene you normally have carbon double bond, sp2 and sp2 as well, right? And carbon double bond appeared at the double bond region around 1600 to 1800, and this is it. So as you can see, we have this graph of the carbon double bond carbon, and we also have this graph of sp2 carbon stretching with the hydrogen atom. So this confirms of the alkene. Next, this is the alkyne. So with the stronger CH bonding, the stretching frequency is getting higher comparing with alkane and alkene. So first of all, mark 3000, and you can see that this is far beyond 3000, appeared at 3300. So this is the characteristic of the sp carbon with hydrogen atom, and you have this stretching. Okay, and as I said, you have to double check with the triple bond carbon, right? Because this is, if this is the actual alkyne, you would see triple bond C, right? So these two characteristic peaks can confirm themselves together that we have the alkyne in the structure. But what about the terminal alkyne? So what you can see here is the what you can see here is the terminal alkyne, right? But how about the internal alkyne? Terminal alkyne is the alkyne that the triple bond appeared at the very end of the hydrocarbon chain. But if you have like internal alkyne, so the triple bond appear inside, right, the hydrocarbon chain. So from here, as you can see, there is no CH bond because this is the internal alkyne. So there is no CH bond characteristic appeared here in the structure, in the spectra. And also because the triple bond here appeared in the middle of the molecule and makes this compound very nonpolar, right? Comparing with the terminal alkyne, the alkyne appear at the very end. So you can have the polarity here in the structure as well. And as I mentioned earlier, that the electronic field of the IR radiation interact with the polarity of the bond. So if this triple bond has non-polar, right, is the non-polar bond, then we have no interaction with the electronic field of the IR wave. So what you can see is nothing here at the triple bond region. So this may confuse you to the alkane, right? So we cannot do anything here. You need something else to confirm that you have the alkyne in the structure. So, and the technique is the carbon-13 NMR, right, that we're going to talk about it later. Okay. So as you can see, there are some drawbacks on the IR, right, but yeah, it's quite an easy way to identify the functional group or functionalities of the molecules. Okay, next. So what about this? It's very easy, actually, right? First of all, Mark 3000. So what you can see here, you have a little peak beyond 3000, a little bit beyond 3000. This is 3100 approximately. And you also have the alkene, the double bond C over here. So you have sp2CH bond, and you have a double bond of the carbon. So this is obviously alkene. Alkene. Right. Next, compound B. And first of all, mark 3000, and nothing beyond 3000, right? And nothing here as well. So this is the alkane, right? You may state it that this is alkane or internal alkyne, right? Because normally you cannot distinguish between alkane and internal alkyne. Right? But if you have more experience, you can figure out the fingerprint. You can confirm that this is the alkane, not the internal alkyne. But that's too difficult, right? So normally if you can see things like this, you may just answer me that this is the alkane, or maybe the internal alkyne. Next, this one. I really love this one, actually. First of all, mark 3000. So as you can see, nothing less than 3000 here. So there is no alkane in the chain, right? There is only, first of all, alkene and alkyne, no? So I will go to the alkyne first. This is the alkyne character at 3300, right? So it's the terminal alkyne, okay? And as I said, if you have the terminal alkyne, you have to confirm that with a triple bond, triple bond C, which is actually about 2000 something, right? But this graph is not very good, actually, because this is 2200. This is the alkyne characteristic stretching, but it's quite appeared in very not very strong signal, right? Actually, if I were the guy who doing this, I would apply more samples in the sample holder to see stronger absorption. But anyway, this is it. What else? I will mark with the blue color here, this is the alkene. Right? Alkene, as I said, it appeared at a little bit beyond 3000, right? So it's the alkene. But this is not a simple alkene, because if you have an alkene, normally you would have the carbon-carbon double bond around 1600, right? But now here in the structure, you have several peaks at 1600, right? This is the benzene ring. So how can I know that this is the benzene ring, not simple alkene? First of all, this alkene, the benzene, you have firstly the CH of the sp2 carbon, and then secondly, at the double bond region, you have 1, 2, 3, and 4. You have 4 peaks of C double bond C, right? This is the second character of the benzene ring. The 4 peaks here is not because you have 4 double bond structure, but because the benzene, when it wobbled, right, it can stretch out and this way, this direction, or it may stretch out like this. So it can be stretched out in many directions, right? It's wobble, the ring is wobble, and the different direction of the wobble of the ring here resulted with the about 4 modes of the stretching of the ring. But yeah, that is quite difficult for you. You have to use kind of physical chemistry to calculate. But anyway, that's the second character. The third character is this. At 1600 to 2000, you will see a little bump, maybe 4 or 5 bump. This bumping is another character of the benzene ring. And the last character of the benzene ring is around 600 to 800 in the fingerprint region. 600 to 800, you can see a strong absorption, normally appeared as 2 sharp or 3 sharp peaks. Okay. If you have these 4 characters, you can be sure that this is the benzene. But sometimes when you have more functionalities, and they may appear around 1600, for example, and it may overwhelm or just dominate the peaks around here at the second and third characteristic region. So you may have seen just only some weak absorption, and yeah, that makes you have less certainty about the structure, right? But if you have all four clearly seen here, you can be sure that this is a benzene, right? So this compound is very small. You have just terminal alkyne and the benzene, so nothing else, right? So you can clearly see these 4 characters of the benzene in IR spectra. Next, the functional group is the ketone and aldehyde that I want to talk about it together. Ketone and aldehyde are very similar because you have the carbonyl group. The carbonyl appeared in the double bond region, but the character of the carbonyl is a very strong absorption because the carbonyl is very, very polar, right? Because oxygen has very high En comparing with carbon atom. So with the very high En, make this double bond very polar and interact with the electronic field of IR wave, IR frequency. So we have the strong absorption of the carbonyl. And yeah, for aldehyde as well. This strong absorption appeared at around 1700. So a little bit higher than the double bond of carbon of the alkene, right? But what you can see here is very strong absorption comparing with the alkene, comparing with the benzene ring, right? The absorption is not very strong. This is very, very strong. So the percent transmittance is dropped down to almost 0. Okay, And if this is the alkene, you have to see the double bond, the CH of alkene as well, right? But there is no CH alkene appeared in both structure, in both spectra, right? Beyond 3000, there is nothing. So if there is the actual alkene, you see something here, right? But there's nothing, right? So this is all the carbonyl. So what difference between alkene, the ketone and the aldehyde? The aldehyde, you would see the characteristic absorption here, 2700 and 2800. This is the character absorption of the aldehydic proton. This is the aldehydic proton, no? So if you have the aldehyde functionality, you will see 2700, 2800 at the slightly the same height, the same absorption intensity, right? This is actually belong to what I would say symmetric and asymmetric stretching, because carbonyl with edge, symmetric stretching meaning that the stretching of this two carbonyl and hydrogen synchronized to the same direction. But asymmetric stretching is this one go this way, this one go that way, and then this one go this way, this one go that way. Right? This is asymmetric stretching. So the polarity, the changing in polarity of these two modes of stretching are different. So we have different position with different wave number of this symmetric and asymmetric stretching, and that's it. Okay, you don't really have to know that. You have to know that we have two wave number of the aldehydic proton at 2700 and 2800. That's enough. Okay. Next, we come to the hydrogen bonding system. So go back to the 3000. You have to mark 3000 wave number, okay, to identify alkane, alkene, alkyl, or to identify the unsaturation of the structure. But now, what you can clearly see here is the broad peaks and very strong absorption. The strong absorption indicates the very high polarity of the functionalities. And the broad absorption, as I said, it is the character of the hydrogen bonding, right? So this is the character of OH and NH, right? OH is highly polar compared with NH. So normally the absorption of OH is stronger than the amine. Okay. Another thing that you can confirm the presence of oxygen in the structure is the CH stretching. CH stretching normally appeared around 1000. Not CH, sorry, CO stretching appeared at 1000 approximately. But this is in the fingerprint region, and it's very, very hard. Right? It's very hard to make sure of the presence of CO stretching here, because normally it's because of the complexity of the fingerprint region. As you may compare with the above structure, right? 1000 is around here, right? And you can see some peaks. So how can you be so sure that this is the CO single bond, right? So sometimes we cannot be very sure about that. But anyway, with the presence of 3300, very broad and very strong absorption here, you can be certain that this is the alcohol. Next, this is the amine. The amine, comparing with the alcohol, as you can see by these two spectra, right? The OH of the alcohol, as I said, is very high polar because of the difference between En value of oxygen 3.44 and hydrogen 2.20. And for nitrogen is less, right? Nitrogen En is about 3.06, which is very small comparing with oxygen atom. So make it slightly lower polarity. So as you can see, this absorption is not very strong, as the OH. So as you can see, it's dropped by this, right? By this. And yeah, this is 3000. You have to mark 3000 first. Okay. So another character of NH here, I would mark it around here. Normally, amine can be divided into subcategories like primary amine, right? Secondary amine, and tertiary amine. So primary amine, you have 2 hydrogen atoms. Secondary amine, you have 1 hydrogen atom. But tertiary amine, you have nothing. You have no NH. So in tertiary amine, there will be no absorption around 3300. So you may confuse us again with the what? With the alkane. And you may also confuse with the ether, right? Because ether has nothing except CO single bond. And CO single bond appeared in the fingerprint region, which is very complicated region. So you may not be certain whether you have ether, tertiary amine, or alkane, right? But anyway, you have secondary amine and primary amine. There are differences between secondary amine and tertiary amine. Normally, amine, you have hydrogen bond, right? So it's broad like this. But the hydrogen bonding system of the amine is not as strong as the OH. Firstly, because OH is very polar, right? So if the OH is very polar, that means H is very positive, O is very negative. The hydrogen bonding is very strong because you have very strong interaction between positive and negative charge. But for amine, En is less, right? So if you have less En, H is less positive, right? And the electron pair of nitrogen, you have only 1 electron pair, right? So the electron density in nitrogen atom is less. So less electron intensity, less electron density and less polarity, less positive charge hydrogen. So the interaction, the electrostatic interaction here is weaker, right? So that means if you have 100 molecules of alcohol, we can be sure that all 100 molecules of alcohol, they have hydrogen bonding together at all times. But for NH, it's maybe just some 50-60% of the molecules that is hydrogen bonding, right? So there will be free NH group without hydrogen bonding, and the free NH group without hydrogen bonding appeared as a sharp peak. So for NH, you will have like a spike here in the peak as well. The spike corresponding to the non-hydrogen bonding environment of NH. So if you have 2 hydrogen atoms, you will have 2 peaks. So count the number of peaks, then you know whether you have primary amine or secondary amine. 2 peaks here belong to symmetric stretching and asymmetric stretching, similarly with the aldehyde. So this is it. You have 1 spike, right? You have 1 spike, so you have secondary amine here in the sample. Next, the carboxylic acid. For carboxylic acid, right, you have 3000 over here again. You have carbonyl. Right. Carbonyl appear at 1700, around that. This is carbonyl. So normally you can see this also in aldehyde and ketone. But for carboxylic acid, you have OH. But OH normally in alcohol, the OH, the zenith of your peak is about 3,300, but the zenith of the absorption of OH of the carboxylic acid is about 3,000. that means your OH is weaker, right? Your OH bond is weaker comparing with the alcohol, because as you know, carboxylic acid can be dissociated, right? It's carboxylic acid dissociated to be carboxylate ion and H plus, so OH bond is weaker. So with the weaker bonding, it appeared on the right-hand side, comparing with the stronger bond appear on the left-hand side. No. And as you can see, the broadening of this peak is wider, right? It's wider than the band broadening of the alcohol, right? This indicating the stronger hydrogen bonding. So it would be different from the hydroxy ketone. So if you have hydroxy ketone, you would have carbonyl and OH of the hydroxy group of the alcohol, but the OH of the alcohol would be like this. Okay. So if you have the OH but shifted to the right, like this, is the carboxylic acid. So you have to distinguish between carboxylic acid and hydroxy ketone. Okay, not very easy, not very difficult. Sorry. Now come to the amide. As you know, the amide here. First of all, go back to 3000. So this is alkane, right? Aliphatic, maybe. The amide, you have absorption of amide, right? Of the ketone, of the carbonyl. But the carbonyl of the amide is dropped to the right hand, 1600 something, right? Different from other carbonyl appeared at 1700, but this dropped a little bit to the right hand side to 1600. That means the carbonyl is weaker than usual carbonyl group. And for NH here, you have two spike indicating the the primary amine, right? But this is not the amine because the absorption is very strong, right? This is very polar, right? It's similar to alcohol actually, but this is two peaks, right? Why? So this means that the amide has stronger hydrogen bonding. No, I would say you have very high polar of NH comparing with the amine. But why? Because if you look at the structure of the amide, like this, your amide can have the resonance structure. En of the oxygen is very high comparing with nitrogen atom. So what you can have here is the electron of nitrogen atom just resonance up to oxygen atom, and you have this structure in state, right? But anyway, the resonance is resonance. Electron can come back to the original position. So this is the resonance structure of the amide. So from resonance structure over here, you can see if you count the number of electrons, oxygen is now negatively charged, and your nitrogen here is now positively charged. It brings the very high polar into your molecules by this resonance effect. So, and if you look at the number of bonds between C and O, it's not purely double bond, right? It's partially single bond by the resonance effect. So the bond, the CO bond is weaker than usual carbonyl group. So the signal is dropped to the right-hand side to 1600. And also, it makes your nitrogen very, very polar because you have charged. And with the very polar, it can interact strongly with the electronic field of your IR wave, and absorption is stronger. That's it. This is the character of amide. So amide and amine are very different, right? Next, the example I was skipped, right? You may go back, look at the examples of the peaks in maybe organic textbook or something. But yeah, this one, I will go very fast. What you can see is you have 1700 something carbonyl group, and you also have 700 and 2800, So this is the aldehyde, okay, for example, and nothing beyond 3000, right? So this is saturated aldehyde, right? Next, oh my, so many things here. So you have 3000 around here. So you have alkane, you have alkene, right? This is the alkene, 3000 something. Right? This is the alkene, and if this is the alkene, you have to double check with the C double bond C as 1600 as well. So this is the alkene, and if you can see the alkene, you have to check whether this is simple alkene or this is the aromatic. So what you can see, there is nothing around 1600 to 800 character. You have no bump around here, and you have only one absorption of C double bond C. So there is no aromatic in the system, right? And this is the alkene. But anyway, okay, I'm not very sure whether this is alkene unsaturated only, or you have this amine as well, right? You have like kind of broad absorption, but not very strong, with one spike, right? One peak, one top peak. So this may be the amine, secondary amine. So you may answer as the unsaturated secondary amine, right? Unsaturated secondary amine. Next, right? Beyond 3000, there is nothing, right? And you have the carbonyl group at 1700, right? And you have strong and very broad absorption here. So this is the character of the carboxylic acid. So without anything beyond 3000, this is saturated carboxylic acid, right? So this is quite straightforward. You know, we go to the next one. Oh, very easy. Nothing beyond 3000 again. So this is saturated something. And as you can see, you have very broad absorption on the left hand, right? Very broad absorption, 3300. This is the alcohol, right? So this is saturated alcohol. Very simple. Now, next, we come to nitrile. Nitrile, as you can see, there is nothing beyond 3000. So this is saturated, only alkane, no alkene, no alkyne. But at the triple bond region, you can see strong absorption of the triple bond here. So if you have strong absorption of the alkyne, you should have CH of alkyne stretching at around 3300 as well. But there's nothing about the alkyne over here, right? So the only triple bond left in your knowledge, right, is the nitrile. So triple bond, right, in your chemistry, you normally knows only alkyne and nitrile. So if this is not alkyne, this has to be nitrile, and that's it. So that's it. Next one. Now come to this one. This is quite interesting as well. First of all, you have to mark 3000. Oops. So as you can see from 3000, you can see something here a little bit higher than 3000, and this is the character of CH of alkene, right? But as I said, you have to confirm it with C double bond C as well at around 1600. But this is a benzene, because 400 to 600, 1400, 1600, you have 4 sharp peak again. Okay, there's 4 sharp peak, but you cannot see the little bump, QT bump around here, because you have a very strong absorption of the carbonyl that dominates the area. right? And they buried the little bond already, right? So you cannot see that. And at 600 to 800, you still can see two sharp peak character of the benzene. So I am quite sure that we have the benzene ring here in the structure. But together with the benzene ring, you also have this strong absorption. But normally, the carbonyl appeared at 1700. But this is slightly less than that, right? Indicating the weaker of the double bond. So what happened with this? This indicates that the carbonyl group is adjacent to the benzene ring. And by appearing very close to the benzene ring here, what you can see is the resonance effect. Because the electron in the benzene ring, because you know from your organic chemistry, right, that the carbonyl group is a good electron withdrawing group for the benzene ring, and then accelerate the electrophilic aromatic substitution reactions, things like that. So these carbonyl group can withdraw electron out of the benzene ring by the resonance effect, like this. So by this resonant form, if you draw it, you would have this kind of structure, right? And you can see directly from this picture that your compound C double bond O, oops, sorry, I would do this. Okay, so your C double bond O bond order is dropped from double bond to somewhere between single and double bond, right? Because of this resonance effect. So you're weakening the C double bond O by resonance the electron from the benzene ring, right? So these two carbonyl and benzene ring, they talk to each other by this resonance effect. Yeah, and by weakening of the double bond, so the signal drops to the right-hand side, to the less wave number comparing with other carbonyl group at 1700. This one is another functionalities, and this is very important. So first of all, at 3000 there's nothing. So this is alkane, right? But not only alkane, what you can see is 1738. What about the number here? This is the carbonyl group. 1700 always be a carbonyl group. But when you see the carbonyl group at beyond 1730, 1730, this is the character of ester, right? Oh, different direction, this direction. So carbonyl of ester appeared beyond 1730 always. No, I would say if you have the carbonyl beyond 1000 or beyond 1730, you can be sure that this is the ester. But when your ester conjugate or resonance with double bond, resonance with the carbonyl, maybe it's dropped down under 1370, right? And it will be more difficult. But when you see something higher than 1730, it's the ester for sure. Okay, now next is sample C here. Again, mark 3000, right? And you see that the alkane, right, is the only alkane. And what you can see rather than the alkane is 1600 something carbonyl again, right? But the carbonyl that less than 1700, indicating the resonance effect, right, is 16 something. You resonance with something else, and it's the amide, resonance with the NH, right? Because you have very strong absorption of NH to spike, right? To spike like this, indicating the primary, right? So you have the primary NH2, right, connecting with the carbonyl. So with the resonance effect, the carbonyl group is not 1,700 anymore. It's less than 1,700 by weakening, right? It's carbonyl weakening by the resonance effect from nitrogen atom, right? And this is the amide. Okay, no? So I will skip all of this, right? So there are many examples you can find from your organic textbook, right? So you're trying to work on that kind of thing, right? And then next video I will show you some more practice problem. Okay, see you again in the next video.